Yeah.
So people are not gonna.
They'll start joining, according to what Michaela said, they'll start joining about 1 minute 2.
Okay.
Yeah, the button should appear for them at 1 minute 2, and I'm monitoring to make sure that does happen too. Because I know the meetings are supposed to as well, but as Beth has discovered, they do not at this time, and that is a known issue. So we'll see what happens with webinars.
The numbers have settled down, so you could probably start at your convenience here.
Okay. I guess it's 5:01 now. So welcome back everyone to the second part of our session on interfaces in the Earth. Okay, I see that there's a chat telling people where to input their questions. So while you're listening to the talks, be sure to post questions. Some of them can get answered live, and I'll turn things over to Shimon right now to do the introductions of our coming speakers.
All right, thank you, Thad, and thank you everyone for attending this session. It's the second part of our session. And our first presenter is Diego Melgar, who is an associate professor at the Department of Earth Sciences, University of Oregon. He holds the Anne and Lou Williams Chair and conduct research on earthquakes, seismology, strong ground motion, tsunami, early warning system, and geodetic imaging. So please, we'll start with his first presentation.
Hello, everybody. Today, I'd like to talk about geodetic coupling at subduction megathrust and how we use that to estimate tsunami hazards and use Cascadia as an example. This is work mostly done by David Small as part of his PhD thesis. I'll start by giving you a high-level view of how we even try to estimate tsunami hazards in general. The end product that we're after is something like this. This is a tsunami evacuation map, where what we're trying to show in these inundation zones is who is at risk from future earthquakes and tsunamis. However, the problem is if these earthquakes haven't yet happened, how do we even know where to draw these lines for these evacuation zones? For Cascadia, this is even harder since we've had no large earthquakes since January 26th of 1700. These maps are important not just for people, but also for building codes and for urban planning. An example from this is the Tohoku-Oki earthquake. Shown here is the Sendai Plain, and this is the Sendai Airport. Whether you decide to build your airport this close to the coast or not depends on your perceived level of expected tsunami hazard. And obviously this is important because these pieces of critical infrastructure are fundamental in the days and weeks following large earthquakes, especially if you need to bring in materials and supplies to the stricken region. So how do we do it? The first step is for your region of interest, in this case the Cascadia subduction zone, you need to guess what you think are the possible earthquakes. Use science to inform your guesses, but ultimately these are guesses. An example from what are currently used as authoritative sources for Cascadia are these t-shirt earthquakes, affectionately called, because the scenarios are labeled extra, large, large, medium, and small. And for each of these scenarios, a certain amount of slip on the fault, shown here by the contours, is assumed. So red is more slip, green is less slip. What these guesses about the future possible earthquakes try to capture is right here at the contact between the Juan de Fuca and the North American plates in this case. What do we think is possible in terms of slip, the relative motion between the plates during the earthquake? Perhaps it's something like 10 meters of relative motion between the two here in the shallow part of the fault, and maybe only 5 meters here in the deeper part of the fault. That's the critical value that we need. And we need to know it not just down dip of the fault, but we also need to know the distribution of these values along the strike of the fault. Are these values the same here in southern Washington as they are, for example, here offshore Vancouver Island? And once you've done that, when you've come up with a family of potential earthquakes, the next step is easy. You take this and you put it into what is called a dislocation model, and you can estimate how much you think the seafloor moves up in the red and down in the blue. And this is an easy problem to solve now. Pretty much any graduate student in seismology or geophysics should be able to go from slip to deformation of the Earth's crust. Now, once you have the amount of uplift and subsidence of the seafloor, what you can do is the critical third step, which is you can turn that into tsunami waves, because if the seafloor moves up and down, well, the ocean moves up and down and generates waves. So we take those values and put them into complicated numerical models like this one, where we can propagate the tsunami over bathymetry and topography and come up with estimates of how much we think different parts of the domain of interest are affected by the tsunami. You do this many times. In the case of the T-shirt earthquakes, 15 times, and you come up with different estimates of inundation for your domain. In this case, for example, here's Willa Bay in southern Washington, 2 earthquakes, earthquake 1 and earthquake 2. These are not exactly the T-shirt earthquakes, these are other earthquakes. But what you'll see is that earthquake 1 produced some level of inundation here in this bit of land, while earthquake 2 produced a lot more inundation. So the final critical step is to make a synthesis of all these different models and come up with this inundation or evacuation map here on the right. For example, someone here made the decision that, you know, even if we think that this middle part of the spit is not easily overcome by the tsunami, it's close enough that we're just going to put everyone on the spit of land in the evacuation zone. It would make no sense to leave whoever inhabits this part of the spit outside of the evacuation zone. So that's the final critical synthesis step. And that's kind of how it works today. But even though we have these maps, like this one for Washington and Oregon in the background here, we're not done, because these maps are always best guesses at any particular moment in time, given the state of the art. And we've had necessarily to use some simplifying assumptions, because there are many, many unknowns. But the most important among them is, what is the range of possible earthquake slip patterns? Those 15 T-shirts. Are those enough to accurately represent the range of what we think is possible? Additionally, computer power used to be quite limited to the point where running hundreds or thousands of tsunami propagation models was considered very difficult. But we can now easily model many thousands of them to obtain statistics and probabilistic estimates of what we think is possible. So that's where we're going today. And the heart of the issue is that most of the uncertainty in knowing what the next tsunami is going to be like arises, in my opinion, from the slip distribution. The tsunami is really sensitive to where on the fault slip is happening. Here are 4 different candidate earthquakes in the Cascadia subduction zone, all of them with slip in different places. All of them will produce a very different tsunami, not just because of the way that the tsunami waves propagate, but also because each of these will produce different amounts of uplift or subsidence at the coast, as is shown here in these curves. And whether the coast uplifts or subsides can also have a significant impact in the hazard. If you subside 2 meters and there's a 5-meter tsunami coming your way, well, that now has turned into a 7-meter tsunami. So all of that variability ends up impacting the hazard assessment. For example, here are 4 earthquakes of roughly the same size, and here's Willapa Bay again, and you can see that there's a great deal of variability ranging from this one where there's almost no inundation, probably because there's no slip offshore, this part of the system, all the way to very bad inundation in this part, and especially here in the south. All of these are from earthquakes of roughly the same size. So given that variability, which one best represents what we think is going to happen next? So what we really need to do is to model tens of thousands of earthquakes and tsunamis, make enough of them that we can sample in a probabilistic sense the range of possible tsunamis, and end up with something called a PTHA, or a probabilistic tsunami hazard assessment. To do this, it's becoming commonplace to use stochastic slip models, like this one here on the right, which are based on the finding by Maya and Baroza that slip is a spatially random field. If you can assume the statistics, and we think we can, of how slip is distributed on a fault, you can very efficiently generate many random slip patterns like this one that end up looking like real earthquakes, quote unquote. We use a specific implementation of the stochastic slip approach called FakeQuakes, which is a set of Python tools that are able to do this on a 3D fault geometry like the Cascadia subduction zone, and they can do this efficiently using just a few tens of cores. So from these tens of thousands of earthquakes, you make tens of thousands of tsunamis like this one, and look at the variability of amplitudes across our coastline. However, there is still one critical simplification and that is that slip is equally likely everywhere if you just start with the homogeneous assumption, which is what most stochastic slip patterns do. What that means is that as you're making this random slip distribution like this one, you are not putting any constraints on where you think slip is more likely to occur. In this particular model, even though it ends up with something that looks like slip to the trench, that was just random chance, because in this particular implementation, slip is equally likely everywhere on this segment of the fault that was selected for modeling. However, we know that there is something called fault coupling. And what that means, and this is obtained from space geodesy mostly, is that wherever you see red is a calculation that shows that that part of the fault is coupled. That means that it's stuck. It's not moving. In this case, we have two general families of coupling for the Cascadia subduction zone, the gamma family that has a lot of coupling all the way to the trench, and the Gaussian family that has less coupling all the way to the trench, especially in the north. Now, conceptually, we understand that shallow coupling, like here in the gamma model, has to be bad news for tsunami hazards, because if the fault is locked here in the interseismic period, it's more likely that it's going to have large slip during the next earthquake. But up to now, we've had no way of formally putting that into the tsunami hazard assessment. So that's what David's been working on. So what he did is he introduces the coupling model as a background mean model into the stochastic slip generation process. The details are complicated, and you can read about them in this paper that David published just earlier this year. But what it means is that we can condition the stochastic slip distributions to put more slip more frequently in places where we have high coupling. So here's a set of 8 magnitude 8.7 earthquakes using the gamma coupling model as the background mean model. And you can see that we end up with frequently shallow slip, not always, but frequently. Contrast that to if you use the Gaussian coupling model, which has less coupling all the way to the trench. Well, if you use that to condition your models, you frequently obtain ruptures that have less slip to the trench. So I'll cycle between them a little bit. Overwhelmingly or frequently high slip to the trench, less frequent slip to the trench between the gamma and the Gaussian models. So that's a way to introduce this measurement or inversion of coupling and use it to condition the kinds of earthquakes that you think are possible. So that's what we did. Now, what are the tsunami impacts of making this choice? Here we compare the tsunami amplitudes up and down the coast. That's what these violins show. They're sorted as a function of latitude using either the blue or the orange, the gamma or the Gaussian heterogeneous background mean model, compared to what we call the 1 centimeter per year, which is for all intents and purposes just no assumption. Slip is equally likely everywhere. And we have roughly about 200 tsunamis per magnitude bin. Here I'm showing you just the magnitude 8.4 earthquakes and tsunamis. Not a whole lot of difference. There's definitely differences between what you assumed and what the resulting tsunami ended up being, but it's overall not a huge difference for these more modestly sized events. However, once you get to the really big events, there starts to be differences, especially in the north, where the gamma and the Gaussian models were very different between trench coupling and no trench coupling. You can see here that the blue, for example, more frequently produces large tsunamis because there's high coupling to the trench than does the orange, which is the Gaussian model, and also more than the red, which is the no assumption, where slip is equally likely everywhere. So there's very definitely an impact from choosing one of the coupling models or from not assuming any of the coupling models. This is one way to look at it. This is just the distribution of amplitudes. Another way to look at it is to make hazard curves. If you make some assumptions about how frequently you think earthquakes are possible of different sizes, and we've made one assumption here, it's possible to make a different one, you can calculate the probability on the y-axis of a certain tsunami value on the x-axis being exceeded that year. So for example, here, there's about a 3 in 1,000 probability of exceeding 1 meter of tsunami amplitude in the gamma or Gauss coupling model, but about a 2 in 100 chance of exceeding the no assumption model has the probability of exceeding that value every year. And this is a little bit of a more informative thing, and especially it's what's used for planning or for hazard maps. And you can see how the hazard curves change significantly depending on what coupling model you assumed or no coupling model, and from south generally to north. And it's also a function of what you call the return period, this annual probability of exceedance. Depending on what level you pick, the effects on the hazard curves is going to be different. It's not always easy to see that from the hazard curves. So here we've picked an exceedance value for you. And what this shows is the levels that have a 2% chance of being exceeded every 50 years for each one of these assumptions. The gamma, locking to the trench; Gauss, no locking to the trench; and 1 centimeter per year, which is no assumption of any kind of coupling distribution. You can see that there's different values of tsunami being exceeded for each one of these models. It's easier to see on the synthesis here on the right, where you see, for example, very, very clearly that the gamma model, which has the high coupling all the way to the trench, more frequently produces very large values of tsunami, sometimes in excess of 7 or 8 meters, compared to the red and the orange. Meanwhile, in the south, rather interestingly, assuming nothing about the coupling model, which is the red, tends to overestimate the hazard. So the converse effect, and actually assuming some coupling model tends to ameliorate, make the hazard smaller in that part of the domain. So these differences are important. They're not just academic, whether it's 1, 2, 3, 4, or 5 meters every 50 years, because these are the kinds of values that you have to choose from when you're drawing the tsunami evacuation lines in urban planning and emergency response. In the case of the Sendai Airport, that might have made the difference between thinking that you could build everywhere outside of this green region, where the airport is, whereas if maybe you had chosen another coupling model, you would have realized that you could only build outside of the red region, so the airport was perhaps in a place that was likely going to be inundated. The same thing is true for these evacuation maps. So these choices end up having potentially big impacts. So which one is it? Is it the gamma model that produces the higher hazards in the north especially, or is it the Gaussian model that has less coupling all the way to the trench? Of course, right now it's not possible to say. Given the network of seafloor geodetic instruments that we have currently, it looks to me like probably the gamma model is more likely given the size and direction that these vectors are pointed at, but it's simply not enough to make that assessment. Right now, the clock is ticking because we're getting later and later in the seismic cycle. So we need a lot more seafloor geodesy if we're ever going to make that decision. So I'll finish here. The conclusion is that this is not an authoritative Cascadia hazards assessment. We are not trying to say exactly what the hazard is and where, but rather we're trying to introduce a formalism for using coupling as prior information into the hazard estimation, which is not something that we've been able to do before. The biggest conclusion is that the choice you make matters. I don't know if the gamma or the Gaussian model are correct, but whether you choose one or the other can have a significant impact in the hazard curves and in the hazard maps. And precisely because that is true, and because we do not know which one of these two models is more likely, is why we need a lot more seafloor geodesy if we're ever going to make that distinction. It remains true that validating these probabilistic approaches is tricky. If I'm trying to give you information about the most likely event at 1 in 10,000 years, for example, if you're trying to build a nuclear power plant, how do we validate that hazard estimate since we only have human timescales to work with is difficult. But we have some ideas about that, and that's something that David is working on, using the Tohoku Oki earthquake as an example. There are other components of tsunami hazards which need improvement, vast improvement that we haven't really talked about, basin crossing events, or perhaps better understood. But for example, whether slip on splays is frequent and whether it plays an important role, or how to deal with the tsunami hazards of landslides remain very, very thorny issues that we still need to think about a lot deeper. I'll stop there. Thank you.
Thank you, Diego. Very interesting presentations. And in the chat, there were a few questions, which some of them you already answered, but maybe not everybody paid attention. So let me read. There was a question by Francine Coloma that asked, with your models, do you also account for tides in your runs?
No, we don't. Thanks, Shimon. But it's possible to do it. The code we use, Geoclaw, which was built by Randy Levesque and others at the University of Washington, can account for tides, for different tidal stages. But for everything you saw here, everything is done with respect to mean sea level, but it's possible.
Okay, thank you. And then by Jenny Sauber, how do you deal with offshore slumping that could cause a local tsunami, such as happened in several places during 1964 earthquake?
Yeah, we don't. I mean, if you ask anybody in tsunami modeling, landslides are the boogeyman. Just look at the Krakatoa collapse a couple of years ago. There is really very little that we can do in terms of anticipating those kinds of hazards, and they can be very, very large. You know, Lituya Bay, I forget the exact number, 100 meters of run up the size of that fjord. So right now, that's a very challenging problem to figure out where the landslide susceptibility is high, what the probability is of those landslides occurring. I don't have a good answer for this. Right here, we're dealing with a much bigger, long wavelength and easier, frankly, problem of the co-seismic contribution to the tsunami. But yeah, landslides are difficult and need a lot of work.
Okay. Another question by Joseph Byron. It's have recent megathrust looked more like gamma or Gaussian? I would assume something like Tohoku was more like a gamma model.
Yeah, that's a great question. David is working exactly on this. Pre-Tohoku, there was a published coupling model by Jack Lovelace and Brendan Mead that looked very much like the gamma model, like the Gaussian model. And now there's also a model that allows the coupling to go all the way to the trench like the gamma model. And you're right, Tohoku looks like it corresponds more to that family of coupling models. What David is doing right now, which is really cool, is he's looking at if you generate these families of ruptures, assuming these coupling models, how frequently, just out of that randomness, would a Tohoku-like slip distribution appear? And from what he's found, which I would have loved to show you here, but I ran out of time, is that if you assume a gamma-type coupling model, it's much easier to make Tohoku-like slip distributions than if you assume the Gaussian coupling model. So, you know, stay tuned at AGU. David will talk about that.
Okay, thank you. Another question by Shelley Olds. Are the seafloor geology data available as a processed product?
I don't know if David Schmidt or Spar Webb or someone from that seafloor geodesy or Ben Brooks are on this meeting. I'm not aware that the seafloor geodesy vectors are published yet. But I assume they will be soon.
Okay, thank you. Another question from Tom Herring. Does the 1700 event give any insight which coupling is more likely?
It doesn't. I thought it would. And we have some work that is in review right now. It'll make it out of review one day. And I thought that, you know, we'd model these thousands of ruptures and compare against what we know from 1700, like the tsunami amplitudes in Japan. We have estimates of that. We have estimates of the co-seismic subsidence here in Cascadia. And it turns out that it's possible to match both the tsunami in Japan and the coastal subsidence with both a gamma and a Gauss type earthquake. So it doesn't close that gap. Yeah.
Okay. There's question keep piling up. So let's do it quickly. Does the rupture velocity matter, and how much would variation of it contribute to the hazard max?
For regional tsunami hazards, Amy Williamson up at the National Tsunami Warning Center showed a couple years ago that the rupture velocity does very little to the regional tsunami amplitudes. Basically, the propagation of the tsunami wave is so much slower than the earthquake rupture propagation speed that essentially the earthquake is instantaneous as far as the tsunami is concerned. Even for a 6, 7, 8 minute long rupture, it's mostly instantaneous, has a very small effect. Only in very peculiar, strange cases of ultra slow ruptures have people shown that there is an effect, but it's very limited for regional hazards.
Okay, thanks. And now a little bit technical question. I have a question regarding your modeling. Is your model made only in Python?
The ruptures are all, it's a Python-based code. The ruptures are, yep. The tsunami modeling code, again, Geoclaw from the UW group, has Python wrappers, but the heavy numerical computation is all Fortran based so that it can be fast.
And now a question from Yehuda Bach. Ideally, one would prepare for the most hazardous event, but you would also have to evaluate cost versus benefit. What is being done by decision makers? And I would like to add something about that. That here in Florida, we suffer from storm surge, and the community over here, they calculate what's called maximum of maximum, and that's how FEMA is actually using this maximum of maximum. So maybe it can be applied also over there.
Yeah, I think different applications make different choices. So scenario type planning is common, where you just try to imagine the worst possible scenario, and you use that for maybe planning how to evacuate a town. So that's useful. But imagining the most outrageous scenario is not useful when you have to build critical infrastructure, especially because the lifetimes of buildings are limited. There's no point in planning for the 1 in 100,000 year event when most buildings don't last 1 in 100,000 years. So, engineers have to make these hard choices of picking different exceedance probability levels and drawing the lines accordingly. Of course, it's still just probability. So if the earthquake happened to occur inside of that time period, you're going to have a hard time, but it's a resource limited world. So you do the best you can with the information that we have.
All right, thank you. And the last question by Jonathan. You mentioned that the biggest uncertainty comes from sleep, i.e. false sleep, but it's actually seafloor displacement, right? Can you make any additional comments on assumptions, complications going from false sleep to seafloor displacement, rheology, model, etc.?
Right. Of course, that's what I mean. I guess the way I see it is this higher order physics, anelasticity in the wedge, for example. People have shown that anelastic deformation in the wedge can matter. All of those higher order things will, of course, contribute to the uncertainty. But every single large earthquake that has happened in the last 20 or 30 years that we've tried to model the tsunami, just simple elastic modeling gets you close enough to replicating things like tide gauge recordings and dart buoys and things like that. So I think to first order, the elastic modeling is enough. Of course, as we get better at computational numerical modeling, we should add these higher order physics. But right now, we have such poor constraints on what really is the structure of the wedge at every subduction zone that it would still just be a guess what kinds of values we put there. But yes, it will matter, of course.
Okay, Diego, thank you very much. It was a very good presentation and good question and answer session. And we'll continue with the next presentation by Clara Chu. Clara has worked at the University Corporation for Atmospheric Research in Boulder, Colorado since 2017. Prior to joining UCAR, she got her PhD at the University of Colorado and completed a postdoc at JPL in Pasadena, California. She's interested in using GNSSR observation to monitor land surface hydrology. So here's the presentation by Clara.
Hello everyone, and thank you for joining in. My name is Clara, and I'm currently a project scientist at the University Corporation for Atmospheric Research, or UCAR, in Boulder, Colorado. Today, I'm going to be talking about how we can use ground-reflected GPS signals to monitor the terrestrial hydrologic cycle. Given that this workshop is aimed at geodesists and seismologists, I thought I'd start with a little background on just what the terrestrial hydrologic cycle is and why we're interested in learning more about it. I'm pretty confident that most of you are actually already familiar with the terrestrial hydrologic cycle, even if you don't even realize it. If I had to guess, I would say that all of you probably know that dirt gets muddy when it rains, plants need water to live, and that snow is frozen water. Those of us who live in the Western US are increasingly aware that the absence of rain creates drought, which creates dry vegetation, which then can lead to wildfire. And a lot of you probably know that many states like Colorado and California rely heavily on having a solid winter snowpack in order to have enough water for the following summer. The amount of snow on the ground, the amount of water contained within the vegetation, and the amount of moisture in the soil are all components of the terrestrial hydrologic cycle. Terrestrial hydrologists quantify the amount of water contained within the land surface and study how and when water moves between the different components of the hydrologic cycle. Doing this is important because we want to be able to quantify and understand how drought evolves, be able to forecast possible flooding. We want to predict how bad a fire season might be, and estimate how much water we'll be able to use in the future. So how does one quantify the amount of water contained within anything? How would I figure out the water content of this tomato, for example? Well, I could weigh the tomato, then dry it out, and then weigh it again. And then the difference between the two weights would tell me how much water was in the tomato. But doing this isn't awesome because now you don't have a tomato anymore, so who cares how much water was in it? Though this is actually something that people do to figure out how much water is in either vegetation or soil, and this is one of the only direct ways to measure the water content of a thing. But increasingly, scientists and engineers are turning to indirect ways to measure water content, where you don't actually have to destroy the thing to know how much water was in it. There are a couple of different ways of indirectly measuring the water content of soil or vegetation, though today I think I only have time to talk about one of them. And I think you will all actually be familiar with this too, now that I think about it. I think most of us have probably cooked food in a microwave before, right? Your microwave oven works because water is really excited by microwaves. Microwaves cause the water in your food to jiggle around, and all that jiggling creates heat, which cooks your food. Though I'm betting most of you knew that already. But microwaves are also extensively used to remotely sense components of the terrestrial hydrologic cycle. Let's pretend that we have a radar that's transmitting microwaves towards something. Let's say some bare soil. The microwaves are going to interact with that soil, with part of the incoming energy being absorbed by the soil, some of it being transmitted through the soil, and then some of it being reflected off of the soil. The extent to which the microwaves are absorbed, transmitted, or reflected depends on the dielectric constant of the soil, as well as the angle of the incoming transmission. The higher the dielectric constant of a medium, the more reflection you're going to get. And as it turns out, the dielectric constant of most natural materials like soil or vegetation is mostly dependent on its water content, with wetter soils or vegetation with a lot of water having higher dielectric constants and vice versa. So if you can measure the dielectric constant of the ground by bouncing microwaves off of it, you can get an idea of how much water is in it without actually having to dry it out first. And this principle has long been used by several different types of sensors, from small probes to satellites, to measure the moisture content of both soil and vegetation. It just so happens that Global Positioning System, or GPS satellites, also transmit microwave signals. And the 32 satellites that comprise the GPS constellation are constantly bathing the Earth in microwave radiation so that your cell phones can direct you to the nearest coffee shop, or so that we can precisely measure the movement of Earth's tectonic plates. There are a lot of researchers who actually use these GPS signals to remotely sense the terrestrial hydrologic cycle. And this field of research is commonly called GPS interferometric reflectometry, or GPSIR for short. Some researchers have also examined how navigation signals from satellite constellations other than GPS can be used for remote sensing, and in that case, the umbrella term is Global Navigation Satellite System Interferometric Reflectometry, or GNSS-IR for short. But I personally only have experience with GPSIR, so that's all I'm going to talk about today. Though from what I've read, GNSS-IR is just a different flavor for the same basic thing. One thing you need for GPSIR is a GPS antenna and receiver, ideally not too far off of the ground, maybe just a few meters. Here I've drawn a pretty terrible cartoon of a typical GPS antenna that you might find as part of the Plate Boundary Observatory, or PBO network. Here's a real picture of a PBO antenna. These antennas are typically about 2 meters tall. They have these cylindrical legs that go really far into the ground in order to be anchored to bedrock, and on top of these legs is that half spherical thing, which is called a radome. A radome is just a cover to protect the GPS antenna from the elements. Here's a picture of what's under the radome, the GPS antenna itself. The PBO network is comprised of hundreds of GPS antennas that are mostly positioned in the western United States and Alaska, and the purpose of these antennas and receivers is to measure the movement of tectonic plates. What GPSIR does is repurpose GPS antennas like the PBO antennas to not only measure tectonic tectonic plate movement, but also remotely sense the hydrologic cycle. And you can utilize this technique with many different kinds of GPS antennas, not just PVO antennas, but these are the ones that I have experience using. What a GPS antenna does is it intercepts transmitted signals coming from the 32 GPS satellites, which are transmitting L-band microwave signals that tend to be either 19 or 24 centimeters long, and these signals are transmitted at all hours of the day. GPS receivers record a type of data called signal-to-noise ratio data, or SNR data. It's a measure of the strength of the received signal relative to the amount of noise in the data. And if we look at how signal-to-noise ratio data changes as one particular GPS satellite rises and then sets in the sky, then we will probably see something like this, where our SNR data is relatively low when the GPS satellite is close to the horizon, and then as the satellite rises overhead, SNR increases, and then it decreases again as the satellite sets. Note the wiggles at the low elevation angles. What are they caused from? In order to explain the wiggles, let's make a vast simplification about the incoming GPS signal. So each GPS satellite sends out these L-band microwave signals, and these signals also look like wiggles. The signal that the GPS antenna wants to receive is called the direct signal, and this is the signal that travels directly from the GPS satellite to the antenna. This is a signal that ultimately helps the GPS receiver determine its position, which is what it was designed for. However, part of the GPS signal doesn't travel directly between the satellite and the antenna. Part of it will first bounce or reflect off of nearby surfaces before it hits the antenna. Here I've represented the direct and reflected signal as two different wiggles or sine waves, or whatever you want to call them. These reflected or multipath signals are usually considered to be a source of noise in GPS data, and engineers try to design antennas that suppress the reflected signal as much as possible. But for those of us interested in GPSIR, we like that reflected signal. One important thing to see here is that the direct signal actually arrives at the GPS antenna first, and the reflected signal comes in afterwards because the reflected signal has to travel a greater distance. The end result of this is that the direct and reflected signals are going to arrive either in or out of phase with one another, depending on the elevation angle of the GPS satellite. And if you remember from maybe high school physics or some other math class, that when you add two waves that are completely in phase with one another, that the end result is an amplified wave. And if you add two waves that are completely out of phase with one another, that the waves will cancel each other out. And this is what's happening at those low elevation angles in the signal-to-noise ratio data. Those wiggles are the result of the interference between the direct and reflected signals. Now you may be asking why there are only these interferences at low elevation angles and not when the satellite is directly overhead. One major reason is the gain of the GPS antenna. It's much higher at zenith than it is off to the sides. In other words, these GPS antennas are designed to be really good at receiving signals that come from higher elevation angles and not so good at receiving signals from low elevation angles. So the interference between the direct and reflected signal will produce the wiggles we see in the SNR data. But what if the reflected surface changes? Remember how I said earlier that bouncing microwaves off of the ground can help us infer the dielectric constant of the surface, which itself is a function of how much water is in the soil or on the surface or in the vegetation? The reflected GPS signal will also change if the dielectric constant changes. So how will the reflected GPS signal change if it rains, which means the soil moisture will increase? What about if vegetation near the GPS antenna grows? Or how about if it snows? These are the scenarios that I'm going to talk about today. After this talk, hopefully you'll understand a little better how we can use GPS signals to infer changes in soil moisture, vegetation parameters, and snow depth in the vicinity of a GPS antenna. And when I say the word vicinity, you're probably wondering what that means. When we use GPSIR to measure snow depth, for example, over what area are we measuring it? Is it a point observation? Does it give snow depth data for many square meters, square kilometers? The answer to that question is, it depends. The spatial footprint of the reflected signal actually changes as the GPS satellite rises and sets in the sky, with larger spatial footprints at smaller elevation angles and vice versa, and taller GPS antennas will have larger footprints. But for the 2-meter tall antennas of the PBO network, we average several footprints from several GPS satellites each day. We can estimate the average daily footprint being around 1,000 meters squared. Let's go back to the conceptual time series of signal-to-noise ratio data that I showed earlier. This time series, which I'm showing as a function of the satellite elevation angle, is a combination of both the direct signal and the interference between the direct and reflected signals. The direct signal component can be approximated as what I have drawn in the middle panel, kind of a parabolic arc. It's going to make things a lot simpler if we remove the direct signal from our signal to noise ratio data, and if we subtract it out, we're left with what I've shown in the bottom panel, just the interference between the direct and reflected signals. That middle part of the interferogram is kind of boring. It doesn't contain any useful information, so we'll just focus on the wiggles here, from when the GPS satellite is rising in the sky. Though you could also use the data at the end of the interferogram, when the GPS satellite is setting, if you wanted. So for the remainder of the talk, this is the only thing we're interested in. This is what those SNR wiggles look like in real life. This is an SNR interferogram recorded from one of the PBO antennas. So how do these interferograms change when soil moisture, vegetation, or snow depth changes? Just looking at SNR interferograms themselves and how they change over time is hard. For example, here are two interferograms from the same GPS antenna that were recorded before and after a rain event. They're a little different, but it's not super obvious how they're different, and the noise in the interferograms seems to get in the way. So what GPSIR does is simplify the interferograms with the following equation. This is the equation for a sine curve as a function of elevation angle with amplitude A, a frequency term, and a phase offset. What you can do is fit this sine curve to each interferogram to estimate these parameters, and then look at changes in the parameters themselves with time. Let's take a look at these parameters, or SNR metrics, as we used to call them. Most of you probably know what amplitude is. It's just how tall the wiggles are. Notice that in our real data, amplitude appears to vary as a function of elevation angle, with larger amplitudes at lower elevation angles. But our SNR equation just basically estimates an average amplitude for each SNR interferogram, and for our purposes that's largely fine. Then we multiply our amplitude by a cosine term, and within that cosine term we have a frequency term plus a phase offset. The phase offset is relatively straightforward. It just describes how the SNR interferogram shifts back and forth. The frequency term is more complicated. In the past, it's been modeled as the sine of the elevation angle of the GPS satellite multiplied by 4 pi times this thing that we call the effective reflector height. Then we divide that by the wavelength of the GPS signal. Effective reflector height seems like a weird term, but what we're talking about is a calculation of the distance between the reflecting surface, or the ground, and then the phase center of the antenna. You can't actually measure this distance physically, but you can estimate it when you fit the SNR equation to your observed data. This means that the frequency of the SNR oscillations is a function of the effective reflector height of the antenna, with taller antennas producing higher frequency oscillations, and vice versa. This is the key concept behind using GPSIR to measure snow depth surrounding an antenna. As the snowpack grows, the height of the antenna relative to the snow surface actually gets shorter, which is going to produce a change in the frequency of the SNR oscillations. So if you see a significant change in the SNR frequency, and you know your GPS antenna isn't sinking into quicksand, you can infer that it has snowed, and actually use the change in effective reflector height as a proxy for a change in snow depth. That's all I'm going to say about this today, because snow sensing using GPSIR is not exactly my area of expertise, but here are a few papers you could check out if you're interested. Something that at one point in time was my area of expertise, though, was using GPSIR to retrieve soil moisture near a GPS antenna. And that's what I would like to focus on now. So let's look at these two SNR interferograms. One was recorded before a rain event, and one was recorded after a rain event, where the soil moisture was way higher than it was before the rain came. And what we're going to do is fit our characteristic SNR equation to both of them. The fitted curves are shown here, where the gray curve is estimated using the observed data from before the rainstorm, and the green curve is estimated using the observed data from after the rainstorm. Now it's a little easier to see that the increase in soil moisture from the rain caused a slight decrease in amplitude and a small phase offset as well. We can make a time series of the phase offset, which is going to be different each day, and compare it to a time series of soil moisture that was measured at the same GPS antenna where the SNR data were recorded. The figure at the top shows soil moisture as a function of time, and we can see that around day of year 253, soil moisture increased a lot really quickly, followed by a slow decrease in soil moisture that starts around day of year 260. The bottom plot is a corresponding time series of phase estimated from SNR data for the same location. On the same day as the big increase in soil moisture, we see a big increase in phase. And we also see that phase slowly begins to decrease around the same time that soil moisture started to decrease. So empirically, we can see that there appears to be a pretty good correlation between phase and soil moisture. And if we see an increase in the phase of the SNR data with time, then we can assume that there has also been an increase in soil moisture in the vicinity of the GPS antenna. What if you have vegetation growing around your antenna? How would you expect SNR data to change in that case? Well, here's one example of how grass growing around a test antenna in Oklahoma changed the SNR interferogram. The SNR data on the left were recorded when there was basically no grass growing, and the SNR data on the right were recorded in the middle of the summer when the grass was really high. There's a pretty obvious change in amplitude, with more vegetation corresponding to a smaller amplitude. So empirically, we can say that phase is going to increase when soil moisture increases, and amplitude is going to decrease when vegetation increases. Does this mean that we can just directly back out soil moisture by looking only at phase data and back out vegetation information by looking only at amplitude data? Not exactly. Remember those two SNR curves I showed earlier, before and after a rain event? We saw that an increase in soil moisture will also cause a decrease in amplitude. So it appears that a decrease in amplitude could mean that either soil moisture increased, or it could mean that vegetation increased. And then there's another problem. An increase in soil moisture will often cause vegetation to grow. So if you're only looking at empirical observations of SNR phase, amplitude, soil moisture, and vegetation parameters, it's going to be really confusing to understand just what is affecting what and to what extent. Because of this, we tried modeling SNR data and how it should theoretically respond to both changes in soil moisture and vegetation parameters, like vegetation height and water content. This was a numerical modeling experiment that adapted a model for bare soil to simulate SNR data, and one of my projects was to add a layer of vegetation to the model. I don't have time today to explain the ins and outs of the model, but if you're curious, this is the paper that explains it. What we did was run a variety of simulations for various soil moisture and vegetation parameters, and first we looked at whether or not our simulations were able to match what we were actually observing in the field. And this is what we found. On the left, we have an observed SNR interferogram in black from a field site where we were monitoring both the soil moisture and the vegetation growth near the antenna. The blue line is what we modeled given the observed soil moisture value during a time when there was no vegetation on the ground. And we see that overall they match pretty well. On the right, I'm showing another observed SNR interferogram in black, but this time from a day when the vegetation at the site had about 2.5 kilograms per meter squared of water in it. What I want you to focus on is the blue line, which is what we modeled when we input the specific vegetation and soil moisture parameters on that day. And again, we see a good match, even recreating the temporary decrease and then increase in amplitude oscillations as we increase elevation angle. We then calculated the SNR metrics for these model simulations and saw how they changed for different soil moisture and vegetation parameters. And we again validated the model, this time using soil moisture and vegetation data from a GPS antenna located in an alfalfa field. The top panel of this figure shows a time series of the wet weight of vegetation, the height of the vegetation canopy, and soil moisture for the site. The middle and bottom panels show time series of observed phase and amplitude data in the open black circles, and the blue dots show what we simulated on the days when we collected vegetation and soil moisture information for the model. This helped us validate our model, as we saw a good match between observed phase and amplitude and modeled phase and amplitude. After we determined that we had a model that was able to recreate what we saw observationally, we used the model to come up with a retrieval algorithm, in this case specifically for retrieving soil moisture in the vicinity of each PBO antenna. If you'd like to read more about the algorithm and learn about the validation of the retrievals themselves, then these are some papers you should check out. We were able to apply our soil moisture retrieval algorithm to SNR data from dozens of PBO antennas throughout the western US, which effectively created a new soil moisture network. Soil moisture, vegetation, and snow depth retrievals coming from the PBO antennas were deemed the PBO H2O network. And although this project technically ended a few years ago, there remains significant interest in repurposing other GPS antennas or even designing really low-cost GPS antennas to do similar work in other parts of the world. So those are the basics of GPSIR and how GPS is helping us understand the terrestrial hydrologic cycle. If any of you have any questions, I'm always happy to try to answer them, so feel free to reach out. And with that, I'll let you get on with your day. Thanks.
Hi, Clara, excellent talk. And there is one question by Tom Herring. Impact of salt in soil affecting the electric constant and thus interpretation of water content. Is it true? Or how does it affect?
Yeah, so I tried to answer it in the chat. That's a great question. For most soils in most situations, salt will only very minimally affect the dielectric constant. If you're interested in looking at the dielectric constant of like salt flats, say in Utah or in Australia, then that's a different story. Salt will then play obviously a major role because in those areas there isn't really soil, it's just salt. One thing I didn't mention is that the soil texture, which is the relative amounts of sand, silt, and clay within a soil, will also affect the dielectric constant, but that's also a second order effect compared to how soil moisture affects it.
Let's see. I have a question. You presented things in a very clear way and seemed very simple to some degree, but I know it's much more complicated. So when we see these oscillations, and from that you detect the soil moisture, etc., how many of them how many satellites do you use in daily observation, and how many points or how many records do you actually calculate to get the information, let's say, for 24 hours?
So that's going to be very site specific. If you have a nice flat site like you're showing in your background, then you'll probably get a lot of very clear SNR oscillations. And the more you average, the better, because as you saw, they can be very noisy. There are more difficult sites that are hilly, or maybe there are, trees or buildings nearby, and you can't use any of the SNR data that's kind of overlapping those areas. So what I would say is that, it depends anywhere between, let's say, 3 and 10 per day per site. But it does involve a fair amount of quality control. Like, you don't want to just blindly try to compute phase from a site without actually going and looking at the site, either using satellite data or actually going to the site.
Okay. Thank you. I think there are more questions coming up. Response of them. From Mike Steckler, what about soil moisture, expanding the soil so you get both soil moisture and elevation change?
So normally when soil expands, it doesn't expand quite enough, at least just for that top layer of soil moisture for us to actually notice. But that's a good question, because that actually relates a lot to how you can use GPSIR to measure changes in tides. So if you have a GPS antenna that's kind of overlooking the ocean, you can use it as a tide gauge. And that is not at all my area of expertise, but for that work, you actually do have to kind of take into account how the surface is changing dynamically as your satellite is rising overhead.
Okay, and there's a question from Susan van der Lee. One might expect that soil moisture would affect the soil's compliance, which could affect the strengths with which atmosphere signals could to seismometer bearing in soil. Have you talked to seismologists who use seismometers to measure soil moisture?
I don't know what you mean by the soil's compliance. So I don't know if I can answer that fully, but yes, there are a couple of people actually in the room right now who are interested in using some seismometers to measure soil moisture, but I myself have not looked at anything.
Susan van der Lee mentioned compliance means sensitivity to deformation.
Okay, that makes more sense. No, I have not looked at that, but that would be really interesting to see.
And there is another question. Everybody say great talk, so excellent talk. How local is the measurement? What are the length scale of spatial variability in soil moisture? Can you interpolate between GNSS sites to get maps of soil moisture?
That's a great question. So in terms of locality, it would be, we like to say that for one GPSIR measurement, you're measuring the soil moisture for about, say, like a football field in size. In terms of length scales of spatial variability in soil moisture, that really depends on where you are. If you're up in the mountains, then you're going to have a lot shorter length scales. If you're maybe in the Midwest with a lot of convective storms, then your length scales would be a lot larger. It really depends on where you are. And can you interpolate between GNSS sites to get maps of soil moisture? Again, that depends. In general, I probably wouldn't unless you have a pretty dense network. Maybe with some areas of the PBO network you could, but you'd want to be careful with your surrounding topography and kind of take that into account with your interpolation.
Okay, I think we reached the end of our session time-wise, and we passed it. So I thank the speakers, the organizers, and all the people who attended the session. It was a very interesting session, both in the morning and in the afternoon. Thank you very much.
Thank you
And I'll
all.
just thank you very much. I'll say we have a 5-minute transition now, and then there will be 4 different e-lightning poster sessions where people will be giving flash talks essentially about half a dozen different posters with time for discussion, interaction, and questions and answers. And then we will see you tomorrow morning, where we'll start with the second plenary session on illuminating transients in Earth processes. Thank you all very much.
Thank you.